Hello, Calc 3, vector calc, right? A lot of times that's a name that people give this course. They'll call it vector calc, or multivariable calculus. So let's chat about vectors. You'll have a really formal definition of vectors and vector spaces if you take a standalone linear algebra course. It's a very big discussion in a course like that. Um, for here, you can think of a vector just as a list of real numbers, right? That's a perfectly good working definition for what a vector is. A list in the sense that they have an order to them, right? So because it's of this focus on vectors, we have a lot of notation and language that I want to introduce for this course, right? For this study of calculus 3 for vector calculus. The main set, if you take the set of all vectors that have a specified number in of real numbers in them. So you could take however many real numbers you want. In this case, I chose n as how many real numbers, right? And put them in a list. Here I'm writing it vertically, but you could write it horizontally if you want, but here I'm representing it vertically. So the set of all um, lists of real numbers with n numbers in them, where each of those is itself a real number. That's called n-dimensional real Euclidean space, or it's an n-dimensional real vector space. Um, the two terms are used, at least for our purposes, pretty interchangeably. And this r to the n, right? Reals to the n, that's the notation for it, right? For the set of all of those. This looks like a lot of really fancy notation, right? But I promise it's something super familiar, especially if n equals 2. This is actually something you've done an enormous amount of work with, right? If n equals 2, what is this? This is saying it's the set of all pairs of real numbers, a1, a2, right? Where a1 and a2 are both real numbers. Well, in this context, instead of using a1 and a2, we typically use the symbols x and y, right? It's just renaming you only have exactly two coordinates, so you don't need really to call it a1, a2, even though you could, right? Instead, we typically call it x and y. So this is the plane, right? The ordinary plane that you deal with all the time, the xy plane, right? Here's x, here's y, and then here's some point, say 2 comma 1, right? If we pick 2 comma 1, there we go, there's a point. Now, in the context of vectors, often we draw an arrow from the origin to that point. It's just a nice visual representation for it, for reasons we'll see. For physics applications, right? A lot of times that'll represent a force, but we'll have other contexts too, where non-physics context, right, where it's useful to think of it that way. So you could just think of it as the point if you want, 2 comma 1, or you could think of it as an arrow that starts at the origin and ends up at 2 comma 1, right? So this is how to think of vectors just as lists of real numbers, right? If there are only two real numbers, then it's something very familiar. But here we're allowing 3, 4, etc., up to n, however large you want these lists to be. So a dimension is just the number of the dimension is just the number of coordinates, right? Is dimension. The number of numbers, right? It's how many real numbers are in your list of real numbers. So for example, if you wanted, you could say that, 1, 6 minus 1, 0, right? This is a four-dimensional vector, right? Another way to say that is you could say that this vector, and also I'm gonna give it a V with a little hat. That little vector hat indicates that it's a vector. Another way you could say that is um, you could say V, this vector, is an element of R4, right? R to the 4, four-dimensional real Euclidean space. There are two ways of saying the same thing. So one vector that is super important, super special, is the zero vector. We're going to use the zero vector all the time for all kinds of different things. The zero vector, often you just write it as just a zero. It doesn't have to be a perfect circle. It actually looks weird with the notability perfect circle. A zero with a hat on it, you can put it like that, or you can, again, list out the vectors right? And put all the zeros there. And that's, if you put in zeros, right, that's the zero vector in R to the n, where you have n zeros in that list. So this is, say in R2, we would think of this as the origin, right? Our origin is in R squared or R2 in the plane, right? In the XY plane, zero is the point 0, right? Super special, important point. Here we're just generalizing that. We'll call it the zero vector. You can still call it the origin in R3 or R4 or whatever, and people know exactly what you're talking about. But also, if you hear us saying zero vector, that's what we're talking about. It's just the vector name for the origin. Now, also notation-wise, I want to mention that here I'm writing everything as columns. You can also write vectors as rows. You'll see, like say this vector v here, I wrote it as a column, but sometimes you'll see it written like this, 1, 6, minus 1, 0, right? Just as a list written left to right. That's perfectly good notation. Sometimes you'll see it like that, but with angle brackets, just to indicate that the perspective is more of like a vector perspective um, than not. That's also commonly used. So if you're looking at different sources, different textbooks, different notes, different YouTube videos, whatever the source might be, you'll see people switch between these notations. Right? Column vector, row vector with angle brackets, square brackets, right? There are lots of different notations for these things. They all mean the same thing. Just like in the plane, right? Say in this 0.2 comma 1, I wrote it as a column vector, but if you were, say, in a college algebra class, you would probably write it as a row vector, 2 comma 1, right? As a ordered pair with round parentheses instead of square brackets. But they all mean the same thing. So don't worry too much. You'll see lots of different notations for this. It's not usually too important. In this course, typically we'll mostly use column vectors, square brackets. That's my favorite way to write it. But we'll see plenty of cases where we do want to write it as a row vector, maybe in a certain context. So that's our notation to get us started. Then, if they just sort of sat there and you couldn't do anything with them, they wouldn't be very interesting, right? But the vector operations, these are things you can do with vectors then, right? These are super where vectors get super fun, where you can start saying a lot. So I have them classified here into 3 batches: unary operations, right? Binary operations, and ternary operations. And ternary, unary, binary, and ternary, what those are, these are these all mean how many inputs does an operation act upon, right? If you've taken any computer science, these might be familiar terms, right? So unary means same prefix like unicycle, bicycle, tricycle, right? Unary means it eats just one input to perform its operation on, right? Binary means it takes 2 inputs to perform whatever operation on. And then ternary means, well, I guess if it was tricycle, it would be trinary, right? But no one says trinary. I actually don't know why. If you know the etymology on that, let me know. I actually don't know the etymology on that. But ternary then is 3 operands, right? So this is how I have them kind of divided up here, these vector operations. A super important unary operation is magnitude. So given a vector, right, given any vector, and no matter how many coordinates it has, right, so v1, v2, up to vn, right, the magnitude of that vector, what it is it's written with absolute value or double absolute value bars. You'll see it written both ways, right? So a lot of books you'll see it written like this. Just write as absolute value, or a lot of books you'll see it written as double absolute value. But they mean the same thing, right? Magnitude, what it is it's the square root of the sum of the squares of the coordinates, right? And essentially what you're doing is you're defining length, right? If you say the length of a vector, right, magnitude is just maybe a more formal way to say the length of the vector. That's what we're defining here. So a nice little example of this is say you wanted the magnitude of that vector 2, 1 that we had up in our little picture up here, right? That first example that I drew up there, 2, 1, right? If you want the length of that vector, how long is that arrow, right? So by this definition, what are we saying? We're saying it's the sum of the squares, the square root of the sum of the squares of the coordinates, right? So this is going to be root 5. And notice all this is really the Pythagorean theorem, right? If you look up here, look at this height is height 2. And oh, I wrote the coordinates 2, 1, but I drew it more like 1, 2. There we go. Doesn't change the magnitude, but it changes the picture a little bit. So the width there is 2, right? This bottom side. Here, I'm going to draw this in red so we can see it a little better. So this bottom side is with 2. This top side is with 1, right? So then if you just do Pythagorean theorem, a squared plus b squared equals c squared on that little triangle, right? Then what does c become? Well, c squared is 5, so then c is root 5, right? So it's literally just Pythagorean theorem if you're in 2 dimensions, right? That's all this magnitude definition is Pythagorean theorem. And so we're just defining, right? So note this is in 2D, right? It's Pythagorean theorem. And it's just defining, for higher dimensions, if you have 3, 4, 5, 6, whatever, you just do that same operation that the Pythagorean theorem tells you to do in 2 dimensions. Okay, so that's magnitude, right? Then there's a super special related definition, which is the definition of a unit vector. And this will just come up so much in the course. So we say that a vector is, and it could be a vector of any dimension 2 or beyond, right, is a unit vector if and only if the magnitude equals 1. And these are going to be super important in defining lots of the things that we need to define in vector calculus. Unit tangent vector, unit normal vector. You'll see unit vectors all over this course. A quick example would be, we would say that this vector, v, 2, 1, right, this is not a unit vector, right? How come? Its magnitude was root 5, right, which is not 1. But say you did this vector, say w equals 0, 1. That is, right? 0, 1, that's a unit vector, right? If you did the magnitude of w, what would it be? It'd be the square root of 0 squared plus 1 squared equals 1. So there we go. There's an example of a unit vector, a non-example of a unit vector, and an example of a unit vector. So, all right, so that's our first unary operation, magnitude, right? Negation is a super important vector operation, right? The negation, so sometimes it's called negation, sometimes you'll see it called additive inverse, right? This is especially in a linear algebra course, you're definitely going to see it called that. So the additive inverse of a vector v is written negative v, right? And the way that you construct it is you just negate every single component of v, right? So if v is, v1, v2 up to vn, then the negation of v, or the additive inverse of v, is the vector that you get by just negating every single component, right? So, for example, if you wanted the little vector v that we were playing with, 2, 1, right, has what as its negation? Negative 2, negative 1, right? And what does this do geometrically? It's kind of nice because it reflects your vector through the origin, right? So if this was v out here at 2, 1, the negative v is going to be down here at -2, -1. Right? Negating the x coordinate will reflect through the y-axis, and then negating the y coordinate will reflect through the x-axis. So you do the two reflections, and you get that symmetry through the origin, right? So that's the negation of a vector. All right. So those are the two most important unary operations, magnitude and negation. Now we get to binary operations. Binary operations meaning operations that take two vectors. See here, I only needed one vector in each case. Like I just had vector v. What's the magnitude of v? Just one input, right? What's the negation of v? Just one input, right? As opposed to now, here we're going to have, instead of just one input, right, for unary, well, this was one input v. Now our operations are going to have two inputs, right, v and w, right? So these are binary operations instead. There are some simpler ones and some more complicated ones. The simpler ones, so addition, subtraction, scalar multiplication, those are pretty clear cut. You'll see they're not too complicated. Dot and cross, there's dot, then there's the products, dot product and cross product. They're quite a bit more complicated. Projections too are there's a lot more going on with those three. So we have three. We'll warm up with these three, and then we'll get to the trickier ones. So for all of these, let's let v1 through vn be the coordinates of v, and w1 through wn be the coordinates of w, right? And what we have here, so for vector addition, you do it component-wise. What does component-wise mean? It means the way you add two vectors is you add, I'm going to add the first component of v to the first component of w, right? And then I'm going to add the second component of v to the second component of w, and so on. And that's how I'm going to get the components of their sum. So you add each component just straight across. And to be honest, this is kind of part of why I like column vector notation better than row vector notation. If you write them in the rows, I mean, you can do it, but then you have to kind of look over here and over here to see like what you're adding. Whereas if they're in columns, you just add straight across. So it's kind of nice. So vector addition, right? This is defined component-wise. And for example, suppose we had that same vector v from before, 2, 1, right? And let's say now w, let's take w to be 3, 0, right? So if we have those vectors, then what is their sum? Their sum then is v plus w 2, 1, 3, 0. We add straight across. So what do we get? We get 5, 1. It's kind of cool pictorially what happens here, right? What you have is you have vector v, right? So I have 2, 1 for this vector v. And then we have this vector w, which is 3, 0, right? So, all right, and you know what? I'm going to change it to 0, 3, just because I just wanted to fit in the picture better. And there you go. You get two examples now. So 0 plus 2 is 2, and 1 plus 3 is 4, right? So let's do now. So there's v, and then here's w, right? W is then 0, 3 on this axis. And now I want to add these together, right? So there are two ways that you can look at it. You can look at it just numerically, like we did, right? You can also look at it geometrically and say this sum 2, 4. Where is it? Oh, it's up here, right? Here's v plus w is 2, 4. That's looking at the numbers. But what happened? Well, we had this vector 2, 1, and then we added this vector w to it. So you can imagine putting a ghostly copy of w over there, right? It's as if you follow the arrow for V first, and then once you complete that arrow for V, you start at that new location and then follow the W arrow, right? So I took W and I translated it away from the origin. It had that same arrow start at the tip of V instead of at the origin, right? And that brings you to V plus W. You can also think of it this way, right? It's just kind of a symmetric picture. You could imagine this, imaginary copy of V, where you first follow the vector W and then you translate V up and to the tip of W and then follow it up to V plus W. That's a great way to look at it as well. And so that's geometrically sometimes how people think of a vector sum, right? Is that the vector sum is it's really the opposite corner in the parallelogram that's determined by V and W. Great way to think of it. It gives good geometric intuition for what's going on. Right. So that's a nice characterization of vector addition, right? So it's the opposite corner of the parallelogram that has V and W as sides, right? So you have V and you're given V and W, treat those as sides of a parallelogram, and then trace your way. And so now you have three vertices already in the parallelogram, right? You have the origin, the tip of V, and the tip of W are three out of the four vertices in the parallelogram. Well, now find that fourth vertex in the parallelogram. There's your V plus W, right? Good way to look at it. Okay. Vector subtraction. Let's look at vector subtraction. What vector subtraction is it's so V minus W is you add V with negative W. So we already had negation as an operation, right? So negate W, take the negative of all the coordinates in W, and then add it to V, right? So that's how to get V plus W, sorry, V plus negative W, also known as V minus W, right? You can also think of it all in one step, of course, by just subtracting all of the coordinates. That's also perfectly valid. So the definition is perhaps not super surprising. The geometry in the picture is really quite nice how it works out. Let's look at these same two vectors, but let's look at their difference instead. So if you look at V minus W, what's happening there? I have 2, 1 minus 0, 3, right? Becomes what? It becomes 2, negative 2. So where does this live in the picture? Well, in the same picture, I can actually use the same diagram. 2, negative 2, how is that coming about? Well, 2, negative 2 ends up being this diagonal in that same parallelogram, right? That's V minus W is going to be that arrow, right? It's saying in order to get to V, what would you have to add to W, right? That's V minus W, right? Because then you can think of it as the W and the negative W cancel, right? Now I said that in words. Let me write that in notation here. You're saying in order to get to V, right? What would you have to add to W? That's the question that we're answering here, right? So that's why you can think of this as V minus W. You certainly, whatever that is, you want to call it V minus W because you want the W and the negative W then to cancel, and then you're left with V, right? So to make it look like the algebraic properties that we know and love about, say polynomials or these more familiar objects before you were playing with vectors, right? This is a property we definitely want to call that vector V minus W. Well, the other diagonal of that parallelogram, that's exactly what that is. That is what you would add to W to get to V, right? Look at this example here where we got 2 minus 2, right? To get from W to the tip of V, you'd have to go over 1, 2 units. And you have to go down 1, 2 units. And that's what we got. It was 2 minus 2, right? So that's I think a nice way to think of vector subtraction, right? You have these two vectors, and you're saying to get from the tip of one to the tip of the other, that's their difference, right? So it's the gap, between the tips of the given vectors, right? Is a good way to think of their difference. You can also think of it as it's the other diagonal. It's the other diagonal in that parallelogram. It is also a good way to think of it. The same parallelogram that we drew to add the vectors together, you can also draw that parallelogram to subtract the vectors. Okay, so there's vector addition, vector subtraction, scalar multiplication. What this is also defined component-wise. And here, what do I mean by component-wise? Well, here you're multiplying. What does scalar mean? I should say that. Here, in this context, scalar just means a real number, a single real number, not a list of several real numbers like a vector, right? Vector means a list of real numbers. Scalar is just a single number. Doesn't get put in any kind of brackets, right? It's just a single number sitting there. 5, right? Scalar. So if you have a vector, right? Again, with any number of components, and then you have a real number, r, so let's call r a real number, then scalar multiplication is r v is defined again, like I said, component-wise, meaning multiply every component by that number r. So it's a lot like negation, right? It's very similar to negation, where negation just negated every single coordinate. If you pick r equal to -1, this is basically negation, right? I think it's worth thinking of negation as its own operation. But you can certainly think of negation as a special case of scalar multiplication where r equals -1. It's a perfectly good perspective. So this is scalar multiplication. The best way to think of this, I would say, is think of it as it's a stretch by a factor of r, right? It doesn't change the direction unless r is negative, in which case it flips it 180 degrees, right? But it definitely leaves it along the same line, whatever vector you started with. So again, for example, say you had if you had this vector v equals to 1, our pet vector that we're playing with here, and let's say r in this case is let's do a few different ones. Let's do r1 equals 5. Well, not 5. That's going to be a pain in the draw. Let's do 3, just so it doesn't take us forever to draw it. So let's do r1 equals 3. Then what do we have? We have r1v equals 6, 3, right? Because I'm just multiplying each component by 3. Let's do another one that's maybe a little uglier. Let's do v equals, still a 2, 1, but let's do r2 equals -1/2. Let's do that. Then what is r2v? R2v is going to be -1, -1/2, right? And again, to see that in the picture, what would we have? We would have v, right, is our vector 2, 1. So 2, 1 is our vector v. And then we're going to multiply this by 3 in the first case, right? So we're going to do 3 copies of this. 1, 2, 3. Same direction, but you're tripling the magnitude, right? So this would be 3v1 or 3v, right? Our scalar r1 would be that vector out there at 6, 3. And then down here you'd have the other way, right? Where, see, it reflected it 180 degrees, or sorry, rotated 180 degrees. Down here you'd have -1/2 v at the coordinates -1, -1/2. Right? So there we have some scalar multiples of vectors, right? Of this vector 2, 1. once you have these operations, addition, scalar multiplication, there's some very popular notation that you'll see, which is called IJ notation, right? These are called elementary basis vectors. So this is one, I is just with the little vector hat is a shortcut for 1, 0. And then J is a shortcut for 0, 1. These are very popular in 2 dimensions, right? So that's if you want 2D, the elementary basis vectors, or you can have I, J, K. You can also have them in 3D, 0, 1, 0, 1, K. So I hat, J cat, J cat, I hat, J hat, K hat is um, these are the 3D elementary basis vectors, right? And there isn't anything in this notation itself to tell you whether you're talking about the 2-dimensional one or the 3-dimensional one. You just have to know from context, right? So it's just in context, are you working in 2D or are you working in 3D? And this is a very popular notation because what can you do? Well, using scalar multiplication and vector addition, you can write any vector in terms of these vectors, right? So our favorite vector that we've been playing with, 2, 1, right? What's a way to write this? You could rewrite this if you want as 2, 0 plus 0, 1. That's sort of separating out the x component from the y component. And then you could rewrite this using scalar multiplication as scalar multiples of I and j, right? See, it's 2 times I plus 1 times j, right? So this is another notation that people use for vectors, right? This is very popular. This is the elementary basis vector notation, right? You can also write, say, just to show a quick 3D example, say we had some vector w in R3. Let's say we had -1, 0, 4, right? What would this be in R3? This would be -1, 0, 0 plus 0, 0, 0 plus 0, 0, 4, right? If you decompose it into the 3 components, right? And the middle one isn't really doing anything, right? So you could keep that there and say this is -1 I hat plus 0 j hat plus 4 k hat, or the middle one you could just toss it, right? And just say this is -1 I hat plus 4 k hat, and just not even write the middle one. Either one's fine, right? They're both perfectly good ways to represent that vector w using elementary basis vector notation. Okay, so there are those binary operations, right? The sort of most basic ones: addition, subtraction, scalar multiplication. Dot, cross, and projection, right? These are quite a bit. There's quite a bit more going on here. When I'm going to write these down, I'm going to define these, right? But they're not necessarily going to look like, oh, I see why you'd want to do that, right? Right? They might look a bit like just esoteric formulas at the moment. Don't worry if that's the case. Remember the first time I saw them, they just looked like kind of arbitrary esoteric formulas, and I didn't really understand what was going on. But that's okay. We're just going to say how to calculate them at the moment. And later, when we talk about properties of these operations, you'll see, that's why that dot product thing is a good idea. Oh, that's why that cross product definition is a good idea. So we'll get to why they are sort of natural constructions, but they won't look natural right now. And that's, like I said, that's perfectly fine. Um, how do you calculate a dot product? Dot product, it's like a component-wise product, except what you do is you take your 2 vectors, and notice here, I'm assuming that these vectors have the same dimension. They're both dimension n, right? Specifically dimension n. And then what do? What you do is you multiply component-wise. So V1, W1, V2, W2, all the way up to Vn, Wn. So multiply component-wise. And then the result, don't build another vector out of it. Like when we did scalar multiplication, you put all the answers in a vector. Don't do that. Instead, add them up, right? So first I multiplied straight across V1, W1, V2, W2, all the way up to Vn, Wn, and then add up the results, right? So that's dot product of vectors. So for example, if we did V is 2, 1, and let's say W is, let's do that same one from before, 0, 3, right? If you take their dot product, right, if you do V dot W, that is what? So I have 2, 1 plus 0, 3. What does this become? It becomes 2 times 0 plus 1 times 3. See, I multiplied straight across. 2 times 0, 1 times 3. And then you just add the results. So you get 0 plus 3 is 3. Right? So their dot product is 3. There we go. Now, what I'm not doing here is what I did before. I'm not drawing a picture, right? I'm not explaining, oh, and this is how to think of it. This is how to visualize it. We'll get to that. That's a big adventure. That'll be for further down the road. Here, we're just saying, what is the notation and what is the definition? How do you calculate it, right? That's our goal here. Here's another example. Suppose I said, given V is 2, 1, and suppose I said W is 0, 3, 1, right? And I asked for their dot product, right? So I have 2, 1 dot 0, 3, 1. Their dot product is undefined. They have different number of components, right? 2, 1 only has 2 coordinates. 0, 3, 1 has 3. So, you could start doing a dot product, I guess. 2 times 0, 1 times 3. But then there's no third component to go with the third component of W. So it doesn't exist, right? So that's just something to be aware of for your dot products. They have to have the same number of components. Okay. Cross product. There are kind of two different cross products. So in 2D, if you have V equals V1, V2, and W equals W1, W2, right? Then people write the cross product V cross W as V1, W2. Well, and here, let me write it this way. V1, V2, W1, W2. There we go. And then, so you could write this as V1, W2 minus V2, W1. This is the cross product. And why is it written with that X symbol? Because that X symbol shows you what to do. Look at what I did. Let me put it in red here. V1, W2. That's this, V1, W2. Minus V2, W1. V2, W1, right? So that little cross, literally a cross product, right? You take the product this way and the product this way, and then subtract them. The minus, I guess, isn't really built into the notation. That's on you. You got to remember the minus, but the notation itself, the cross product notation, shows you what products to do, right? Now here, be aware. Sometimes people will consider. Well, let me define the 3D one first, and then I'll back up and talk about how the 2D one is sometimes discussed. So for the 3D one, it looks a lot like what we just did in 2D, but you're going to do it over and over and over again. So for the 3D one, here's the definition of a 3D cross product. In projection, you gotta make some space here. Thank you. So for the 3D one, here's the sort of convoluted looking definition. You're gonna do what we just did for the 2D one. But you're gonna do it 3 times. And the way you do it is as follows. Our result here is actually going to be a vector, right? We're going to have 3 components in our vector. And what we're going to do is you're going to do a 2D cross product using the 2 components that you're not calculating. Meaning, if I want the answer for the x coordinate in a cross product, use the y and the z. Do a cross product. See, for the x, I'm going to use the y and the z. So that's what I'm going to put up here. I'm going to put V2W3 minus V3W2. Right. Okay. Then, when you want, I'm going to erase the little box here just because it's going to get cluttered quickly. And I'm going to erase this x because, again, it's going to get cluttered quickly. That's why this is a video and not static notes, right? If you keep writing on top of it, it looks like a bunch of chaos. Now, for the y, I'm going to use the x and the z. But did you see the order I drew those lines in? I drew them in the opposite order that I drew them in for the x. I drew them like this. It mattered. Here you're going to do V3W1 minus V1W3. How come? Why do you do it in the opposite order for the y? I'll tell you when you're older. Not much older, maybe a couple hours from now, maybe a couple minutes from now if you go watch the next video. But it turns out that for the cross product to have all the nice properties that we want it to have, you just need to do it the opposite way on the y coordinate, and it'll have lots of beautiful properties that would not be there if we didn't. So, like I say, you'll thank me later for having done it in this awkward way. Now, for z, you're going to use x and y. And here, I returned to the order I drew it in the x case. There we go. Right, there's the z. So there we have our 3 formulas, right? Notice once again, it's the 2D cross product, but we did it 3 times. One really nice construction that people often do here is notice this is what? If you write it in IJK notation, right, this becomes let me write down. So this would be V2W3 minus V3W2 I hat, right? And then plus V3W1 minus V1W3 J hat plus V1W3 minus V3W1 K hat, right? This has a nice way to represent it. Really need more space here. There we go. What's a nice way to represent this? If you've seen determinants before, you can represent this as a determinant. If you haven't, don't worry about it. But if you've seen determinants, it's a good way to remember the formula. So you do I hat, J hat, K hat in the top row. And then if you do cofactor expansion, where V is the second row and W is the third row, that's exactly what you get, right? This is what's written up there. That's just the cofactor expansion of that matrix, right? So it's a nice way to represent that. People often will remember the determinant for the cross product formula by writing down this determinant, right? Because a determinant, that matrix, it's a clean set. You just put IJK across the top, you put vector V in the middle, you put vector W in the bottom, and then you do a determinant. So if you're familiar with determinants, great. That's a nice way to remember the formula. If not, you can totally just do it this way, the way I first did it, where you just think of it as 3 separate cross products, and you could jump right to that formula. Either way, it doesn't matter which one you do. So let's do an example, right? Let's do a quick example of a cross product calculation. And here's what I wanted to say about the 2D one. Some people don't think of the 2D cross product as an operation at all. They just always say that it's a 3D cross product, and they just treat it like this. So the 2D one, if you want, you can think of the 2D one. So 2D as a special case of 3D, right? You can think of it that way if you want. You can write it like this. You could say that if you have V cross W and they only have 2 components, right? Then what you can do is you could say equals, I'm going to put equals in quotes here because it's not really equal. It's kind of a different perspective. You could say you could say that these vectors V1 and V2, V1, V2 in the XY plane, and then W1, W2 in the XY plane. You could say you could think of them as actually being 3D vectors whose Z coordinate is 0. So you can think of it that way, right? You could say, here's V1, V2, this vector V, which is V1, V2 in the XY plane. You can identify that with, imagine you're in 3-dimensional space. You have an X axis, a Y axis. So I'm taking the XY plane and holding it flat as an XY plane, and now I'm giving it a Z axis. You can say, oh, it's this little vector V down in the XY plane whose Z coordinate is 0. Right? So you can identify that vector V, that's a 2-dimensional vector, with another associated 3D vector, which we can still call V, because we didn't really change it. All we did was give a 0 to the Z component, right? And do the same thing with W. So sometimes what people do then is they'll say the 2D, there isn't really a 2D cross product. 2D cross product is really just 3D cross product, where you now do the cross product that we just defined up above. What happens if you do the one that we just defined up above, the 3D cross product? If I do these 3 cross products, what do I get? Well, I'm going to have in that first component, the X component, right? I'm going to do this red formula that I wrote. And so this is going to be V2 0 minus 0 W2, right? And then I'm going to do that green construction, right? Which is going to be this minus this. So I get 0 V1 minus, 0 W1 minus V1 0. And then I'm going to do the blue construction, right? For the Z coordinate, I'm going to do the X and the Y. And do this, right? So I'm going to go V1 W2 minus V2 W1. Haha. So what does this end up being? Well, look at the first two. They're just 0. So you get 0, 0, and then V1 W2 minus V2 W1. So what happened there? The 2D cross product is, see, that's this formula. That formula is that formula, right? So sometimes people define the 2D cross product to just be that number, V1 W2 minus V2 W1. Sometimes people want it to be a vector, 0, 0, V1 W2 minus V2 W1. You'll see different conventions in different sources, right? Whether a cross product of two-dimensional vectors, sometimes you'll see it's just that people just say it's undefined, right? That, oh, cross product only works for 3 dimensions, right? Sometimes you'll see it where it's defined to be that number, V1 W2 minus V2 W1, and sometimes you'll see where people say, no, it's this vector. It's actually a vector. It's 3D, 0, 0, V1 W2 minus V2 W1. There's no right or wrong. Just be aware of what's the convention in the source that you're working from, and they're, hopefully you can see how they're all kind of equivalent. just how you want to define it, really. So, all right. Let's scroll on down because that shade of red and pink, looking at those together, is just hideous. So let's move along and do a short example of calculating a cross product. So here's a little example. So if we do, say I wanted the cross product of 1, 0, 1 with 2, 3, minus 1. Right, let's do their cross product. Let's see what that gives us. So here, again, we're going to do, what's the red formula? It's this times this minus this times this, right? So that's going to be 0 times -1 plus, sorry, minus 1 times 3. Right, then we're going to do our green formula. I think green was next, right? Yeah, green. Then we'll do our green formula is going to be this times this minus that times that. Right. So that's going to be 1 times 2 minus 1 times -1. Then we'll do our blue formula, which is going to be this times this minus this times this. So it's going to be 0 times -1 minus 1 times 3. And when you put that all together, what do we have? I have -3. Now you just do the arithmetic, right? So I have -3, then I have 2 plus 1 is 3. Then I have 0 minus 3. So again, -3, 3, -3. There we go. There's the cross product of those two vectors. All right. So that's dot and cross. And now, like I said, if this seems like, oh my God, this is so convoluted, why are we doing these dot and cross products? Yeah, they seemed convoluted and arbitrary to me too the first time I saw them. Hang in there once you see the properties, these beautiful properties, the really nice geometric properties that are satisfied by dot and cross. Then you'll see, oh yeah, okay, these are nice constructions, right? Projections. This is also a really, really important binary operation. So you have two vectors, you have a vector v and a vector w. So these also need to be the same dimension, right? So if if v and w in this case are both in the same say of the same dimension, right? Then the projection, right, of v onto w is, it's going to be kind of a crazy definition. So projection of v onto w, it's going to be defined using dot product and scalar product. So we're using older binary operations to build newer binary operations. Here's what it is. So it ends up being this crazy looking definition. So it's going to be v dot product w divided by w dot product w scalar multiplied by w, right? So it's a pretty complicated formula. What's cool about it is this gives the shadow cast by v onto w. So it's called the projection. It's like what a projector would do, right? If v were a screen or a movie screen, right? And then w is the projector. Well, sorry, and you have a projector shining at that screen, right? Then v, it's a shadow cast by v onto that movie screen. So it's a very very cool construction. Why this crazy scalar product and dot product construction calculates it, not clear at the moment. Like I said, I'm just these more complicated operations, I'm just defining them. I'm not proving anything about them. I'm just getting us to where we can work with them, understand the notation, calculate with them, right? When we prove the properties of these, you'll get a lot more intuition as to why these definitions work. So here's an example of this. Let's find the projection, our two favorite vectors that we played with for most of this exercise. Let's find the projection of, let's do V R, um, let's do this vector onto W, 2, 1. So the same vector that we've been working with, I switched the names of them, right, just to, well, you'll see. Because because I want 2, 1 to be the ground. So here's what we're saying. We're saying, or the screen, right, the projector screen. So here's vector W. So here's how you imagine it. Imagine it as W is defining the screen, the screen that's being projected onto, right? So then at distance infinity across the room over here is the projector, right? So this is shining, there's some giant projector over here and it's shining light like this onto this screen. And it's set up, of course, that these are all perpendicular, right? The rays are coming perpendicular, the light rays are coming in perpendicular to W. So you can think of it as W is the ground and this is the sun, or you can think of it as W is a movie screen and this is the projector back there, right? Then we have V, and V is going to be this vector 1, 2, 3. There's the vector V 0, 3, and then I want to say, okay, my projector here is shining these rays perpendicular, right? See, there's a light ray coming in perpendicular. So now I'm going to put in black right here. This is the shadow. That's what I want, right? So that shadow, that's the projection of, geometrically, it's the projection of V onto W, right? And that's what I want to calculate. Now, how do I calculate it? Well, I gave the formula. This is a nice formula using dot product that calculates it. You can actually do it using trig. You can do just a big ugly trig problem and set up a bunch of SOHCAHTOAs and Pythagorean theorems and all that kind of stuff. You can do it that way, but it's actually way easier with dot product. So let's do it this way. So what is our calculation? So we're going to do V dot W. So here's V dot W over W dot W. Scalar, multiply that by W. Right? I'm just plugging everything into that projection formula given above. And I challenge you this semester to, while saying W dot W, to do that without ever once accidentally saying WW dot. I about 10% of the time at least, I accidentally say WW dot for obvious reasons. But just muscle memory in the mouth, right? So now what's here? I have the dot product up top, 0 times 2 plus 3 times 1. The dot product in the bottom, 2 times 2 plus 1 times 1. 2, 1 is here, right? Then what do I have? I have 3 on top. I have 5 on the bottom. Right? And here I have 2, 1. So what does it become? It becomes 6/5 over, there's 6/5 comma 3/5, right? There we go. There's the projection. So we just found the projection. That little shadow right there, it is in and of itself a vector, right? And notice it kind of makes sense how it worked out. 6/5 comma 3/5. There's still a 2-to-1 ratio between the x and y coordinate, just like there was for W. W was defined as 2 in the x and 1 in the y. It still has the same ratio. It's just a shrunken version of W, right? Which makes sense because all I did was scalar multiplication, scale of W, right? W times a scalar. So it can grow W longer, it could shrink it shorter, it could, reflect it 180 degrees, but it can't turn it at some angle other than 180. So it makes sense that it kept that 2-to-1 ratio because it was just scalar multiplication, right? And if you notice it, right, so that this vector V casts kind of a short shadow, which makes sense because V was pretty tall compared to W, right? It was V wasn't at some low angle where it was going to cast a really long shadow. It was casting a pretty short shadow because V was kind of standing almost straight up with regards to W as the ground. Okay, so there we go. There's calculating a projection. Ternary operations, there aren't a ton of these, but there's one that comes up in Calc 3 and it's kind of cool. It's called the triple scalar product. So the triple scalar product is if you have V, so if you're given V, W, so let's say U, V, and W all in R3, right? So these are all three-dimensional because we're going to use a cross product to define it. So we want cross product to be defined. If you view V and W in R3, right, then their triple scalar product is defined to be U dot V cross W. That's their triple scalar product. So if you combine a cross product with a dot product, then you get the triple scalar product, right? So this is something you can calculate. Again, I'm not going to show right here, why is this interesting? What does it tell you? Nothing like that. I'm just mentioning that this is something you can do with vectors. We'll see later on as we prove more properties of these, what this does and why it's interesting. Now, here's something to note. This is why I like the triple scale product. I think it's a good place to pause and focus on types of objects. Note why is this well defined? This works because when you do V cross W with two three-dimensional vectors, what does that return? This was a vector, and it returns a vector, right? The end result of a cross product of two three-dimensional vectors is another three-dimensional vector, right? And then U is also a three-dimensional vector by definition. Then I can take the dot product of a three-dimensional vector with a three-dimensional vector, and that's going to give me a scalar, right? That's going to give me just a number. Because when you do a dot product of two vectors of the same dimension, you get a scalar, right? As opposed to say you tried to define the triple scalar product a different way. Say you tried to combine dot and cross by doing U cross V dot W instead of the other way around. Instead of doing U dot V cross W. This would be garbage, right? This does not exist. How come? Here, you'd have V dot W returns a scalar. It's just one number, right? So now here you have a 3D vector and you're about to do a cross product. Well, you can't do a cross product between a 3D vector and just one number. The cross product has no idea what to do. It's like, hey, I was expecting three numbers to cross product with those three numbers, and you only handed me one number. Therefore, it does not exist, right? So, like I said, I'm not going heavily into the geometry of the triple scalar product, but I think it's worth noting that, say a ternary operation that's defined to be the dot product of a cross product, perfectly valid ternary operation. A ternary operation defined to be the cross product of a dot product doesn't make any sense, right? Just undefined. So it's good when you'll see throughout the semester we're going to be combining these operations: dot, cross, scalar, addition. We're going to be combining these in every which way: up, down, sideways, left, right, backwards, forwards, diagonally. And as we do that, keep these types in mind. Like, oh, if I do these two operations, what kind of object do I get? Is that valid to feed to the next operation, right? It'll help you remember formulas. It'll help you always write down formulas that are valid, right? So, okay, great. So there's our introduction to vectors. Lots of notation here, lots of new words here, right? Hang in there as you do practice. It's probably a little bit overwhelming, right? Notation overload, vocabulary overload. As you, of course, practice is key, right? As you do lots of practice problems with these words and notation, it becomes more familiar, just like anything. All right, thanks. See you in the next video.